All right. As with many things in this class, we can figure out the concepts, but there's going to be some math that goes along with it as well. So, with problems involving friction, basically there are going to be three equations that we're going to be dealing with. One is the frictional force equation, which we just learned to get today. Friction is fun, F-U-N. And by the way, I don't know if I said that. That's the reason why friction is fun. That's why we say that, because the equation itself looks like fun, F-U-N. You'll also use this equation to find the force of gravity. And remember, this is the same thing as the weight. Sometimes you'll also use sigma F equals ma, which is Newton's second law. If they give you the coefficient of friction, it's a dead giveaway that this is probably what you'll use. To find the weight or the force of gravity, it needs to be this. And keep in mind that usually the force of gravity is equal to the normal force, which is an important thing to find because it appears in this equation. Sigma F equals ma will be an important equation to use, especially when you have acceleration in the problem. When you have acceleration in the problem, sigma F equals ma is a good one to use. So let's read this problem. You have a 60 kilogram cart and you're going to push on it, and I want you to cross this out because I don't know how much force we're applying yet. That's what we want to find. 60 kilogram cart, I know that's my mass. These numbers, mu s and mu k, mu is spelled mu. Mu s and mu k, s and k stand for static and kinetic, and the mu is the coefficient of friction. So they gave us the static coefficient of friction and the kinetic coefficient of friction. We want to know how much force it takes to get this cart moving. And once we get it moving, we want to know how much force it takes to keep it moving at constant velocity. It's a very important thing to remember. All right, when you have a problem involving any forces, it's very important that you always draw a free body diagram. All right, so we're on planet Earth. That means we have a force of gravity, and we're sitting on a surface. We could assume that if we're talking about friction. And if you're talking about friction, at least in this class, there's always going to be a normal force. We're not talking about air resistance friction. That's something different entirely. If we're pushing, a push or a pull is an applied force, and we're fighting the force of friction because we are indeed talking about friction today. As far as my givens, I know my mass is 60 kilograms. I know my static frictional coefficient is 0.08. There's no units to that. And I know my kinetic friction coefficient is 0.05. We got that from right here. And if it says how much force does it take to get the cart moving, that means how much force do I have to push with. So I'm looking for the applied force. That's what they're asking for. How much force does it take to push this cart and get it moving? Okay. So the first question asks about getting the cart moving. The cart is at rest. The cart is at rest, and so we're going to get it moving in the opposite direction. To get it moving, I must overcome a force of friction. And remember, there's two types of friction, static and kinetic. If the box is initially stationary, we're dealing with static friction. That's the force we need to overcome to set an object in motion. So I have to overcome static friction here. And let's stop and think about something really quick. Let's say that I find the force of static friction to be, say, 25 newtons. Okay? And imagine that we might push with a force of exactly 25 newtons. And if this is 25 newtons and this is 25 newtons, the question is, do we get any movement? And the answer to that question is no. Reason is because if both are 25, those are balanced forces. Balanced forces means we cannot have any acceleration. Acceleration is a change in velocity, so that means if I have balanced forces, my velocity doesn't change. To begin with, my velocity is 0 to start out with. That means it stays that way. So in other words, I would write down, if I apply a force exactly equal to the force of static friction, I get no movement. Box doesn't move. What that means is I must apply a force that is just greater than that force of static friction. So if it's 25, as soon as my force goes just over 25, like 25.00001, whatever you consider to be over 25, that's when you get the unbalanced force and it starts to move. So to get it moving, in other words, we will have acceleration right here. We will have acceleration to get it moving because it's going from 0 to non-zero. So in order to know how much force to apply, we need to know what the force of friction is that we're working against. And to find that, once again, remember I told you, if they give you the mu, the coefficient, that's a pretty dead giveaway. You're using this equation. So the force of static friction equals mu static times the normal force. The static mu we got right here, 0.08. And the normal force, do we know the normal force yet? Well, we don't quite, but let's look at the free body diagram and consider force of gravity and normal force. These two, remember it said it up here, the normal force is usually the same as the object's weight, and it is here. So in order to find the normal force, we have to now find the force of gravity. And remember, these are our three equations that we're dealing with. Force of gravity is mass times gravity. The mass of this cart is 60 kilograms, and lowercase g is the acceleration due to gravity, which we all know to be 9.8 meters per second squared. 60 times 9.8 gives me a gravitational force of 588 newtons, and that is equal exactly to the normal force because we have balanced forces in the y direction. It's not falling through this surface that we're on. So that 588 will be able to go right in here for the normal force. And now it becomes pretty simple. 0.08 times 588, if you multiply that together, you come out with a force of static friction of 47 newtons. I'm not quite done yet, because remember I said if I push with exactly the same force as the frictional force, I get no movement. So the answer that I would write is that the applied force that I must use has to be greater than 47 newtons in order to get the cart to move. So that's the answer to the first question. How much force does it take to get the cart moving? Second question is, once we get it moving, how much force does it take to keep it moving at constant velocity? Okay, so I'll write this. To keep it moving, we must overcome a force, or we're fighting a force at least. And that force is friction, but this time it's moving. We're sliding the box. And if it's moving or sliding, we're going to use kinetic friction. So I've got to overcome or fight kinetic friction. If we are moving at constant velocity, that's a very important thing to know, because that means we have no acceleration. And if we have no acceleration, that means now our forces are balanced. In other words, my applied force this time must be exactly equal to whatever the kinetic frictional force is in order to get it to move at constant velocity. If my applied force is greater this time, remember my applied force was greater than the frictional force here, and I got acceleration. I got the box to go from 0 meters per second to not 0 meters per second. I changed the velocity. Now here, I don't want the velocity to change. I want constant velocity, which means I want no acceleration, which means the forces must be balanced, which means the applied force has to equal the frictional force. And once again, I just need to know what the frictional force is. And I will calculate it the exact same way in this one. The kinetic frictional force equals mu k times the normal force. So now it's the same exact equation, except I use a different coefficient. That's why they gave me two coefficients. The other one is 0.05. The kinetic is the one I will use for this problem. And the normal force I need now. Does the normal force change from here to here? The answer is no, it doesn't, because the mass of this box didn't change. At least they didn't tell us it did. And gravity certainly does not change. So this 588 will be the same normal force we use both times. And 0.05 times 588 gives us a kinetic friction force of 29.4 newtons. And that has to be exactly equal to the applied force to get us moving at, or to keep us moving at constant velocity. A couple of things I want to show you. Notice how similar the coefficients of friction were. They were only 3/100ths off from each other. And we had the same normal force, where is it? We had the same normal force, 588, in both of these calculations. And each time that meant, or that calculated into a force that was actually pretty drastically different, 47 versus 29.4. That means that this coefficient of friction can have a pretty large effect on changing the force of friction. In other words, the surface you're on makes a huge difference. I'd much rather walk on a tile floor than on ice. That's a huge, huge difference in friction. Also, I want to highlight what we talked about with static and kinetic. This was the force of static friction. This was the force of kinetic friction. And we said static friction is always higher than kinetic friction. And that's what it came out to here. Static friction much higher than kinetic friction. For every single type of surface, that will be true. Static friction is higher than kinetic friction.